Hello and welcome to this episode of Physical Attraction, where we're continuing our series on cosmology. In this episode, we'll be talking about some of the contradictions that have come up in the cosmological theory developed so far. In the last few episodes, we've talked about the interplay between observations and theory in trying to understand the structure of our universe at large. We've discussed how Einstein's theory of general relativity gave rise to a theoretical framework that would explain how space and time could expand, and solutions to the Friedmann-Robertson-Lemaitre-Walker equations, which were derived from that, which could give rise to universes with a whole range of different cosmologies. And we talked about how Hubble's observation of the redshifts and receding galaxies proportional to their distance. We've discussed how Einstein's theory of general relativity gave rise to a theoretical framework which would explain how space-time could expand, and solutions to the Friedmann-Robertson-Lemaitre-Walker equations, which were derived from Einstein's general relativity, that could give rise to universes with a whole range of different cosmologies and behaviours. And we've talked about how Hubble's observations of redshifts and galaxies receding at rates proportional to their distance was seized upon by these same theorists as evidence that we were, in fact, in a universe that could be described by these equations, one that was expanding over time. Just because these jigsaw puzzle pieces seemed to fit together so perfectly, though, it did not mean that all of the scientists were willing to embrace the quite radical philosophical conclusions that the universe was expanding and that it must have had a beginning and perhaps a rather explosive one. And when I say philosophical objections here, it's not just a case that some scientists didn't like the idea that the universe had to have a beginning, or indeed that eternal expansion would drive you towards that cold, final, steady state that we've discussed in previous episodes, where the distance between all adjacent objects in the universe becomes too vast to ever be crossed by signals of light, and communications between all different parts of the universe are lost forever, a sort of endless expansionary hell. Some scientists were doubtless concerned philosophically with the implications for the very beginning and the very end that came out of Einstein's theory, but there were other reasons to dislike it. We've discussed how even Einstein, in unpublished work, was still looking to see if there might be some solution that would explain the observations with a universe that was still steady state. But there were other issues with the theory of the universe as it existed in the 1930s and 1940s. For example, if you tried to estimate the age of the universe based on the Hubble constant, the rate of the universe's expansion, as Hubble had measured it then, you got a figure of a couple billion years old. This was based on the idea that the universe was around 2/3 the age of 1 over the Hubble constant, which was the theoretical calculation at the time. This problem, though, gave a serious issue because geologists like Arthur Holmes had figured out how to effectively date the Earth using the decay of radioactive isotopes. By measuring the relative quantities of different uranium isotopes in rocks on Earth, they'd figured out that the Earth was containing rocks that were 2 billion years old, and Holmes by the 1940s was suggesting that Earth could be 4.5 billion years old. The Earth could not be older than the universe that contained it, so for advocates of the steady-state theory, this was proof that the idea of a Big Bang and all of these theoretical ideas were clearly wrong, giving you an inaccurate estimate for the age of the universe. Alongside this, our best estimates for the age of stars also seem to be substantially older than the age of the universe at this time. In fact, as our understanding of the physics of stars was improved and more stars were being observed, the estimated age of the stars seemed to get older and older, with many stars that were observed suspected to be much older than 1 billion years. Obviously, the idea that the universe is somehow younger than the stars that it contains was also a contradiction, which blew another hole in the side of the nascent Big Bang theory that the universe had an origin date. There was another rather confusing problem that was showing up with trying to interpret the results at this time. Remember the nebulae, the other galaxies that Hubble was measuring? Because the redshift in the frequency of light from these far-off galaxies is proportional to their distance away from us, as the light is effectively being stretched along its journey as the universe expands, you can use the redshift to determine distances to galaxies as well. When this was done, something strange was found. If you assume that all the galaxies are roughly the same size as the Milky Way, then it seemed like the galaxies were too close and too faint for it to really make sense according to this model. You could compare their apparent brightness to the distances calculated from redshift, and you ended up concluding that the galaxies must all be much smaller than the Milky Way, and substantially closer to us. If you're getting used to how physicists and cosmologists think, you can see why this too is objectionable. It goes against the cosmological principle and the idea that we're not really that special. If every other galaxy is smaller than the Milky Way, then it must mean that we happen to live in the biggest galaxy in the universe, which seems like a bit of a mighty coincidence that would again need to be explained, or perhaps a suggestion that our theory is possibly not correct. Arthur Eddington wrote about this in 1933. He said, quote, "The lesson of humility has so often been brought home to us in astronomy that we almost automatically adopt the view that our own galaxy is not specially distinguished, not more important in the scheme of nature than the millions of other island galaxies. But astronomical observation scarcely seems to bear this out. According to the present measurements, the spiral nebulae, though bearing a general resemblance to our Milky Way system, are distinctly smaller. It has been said that if the spiral nebulae are islands, our own galaxy is a continent. I suppose that my humility has become a middle-class pride, for I rather dislike the imputation that we belong to the aristocracy of the universe. The Earth is a middle-class planet, not a giant like Jupiter, not yet one of the smaller vermin like the minor planets. The Sun is a middling sort of star, not a giant like Capella, but well above the lowest classes. So it seems wrong that we should happen to belong to an altogether exceptional galaxy. Frankly, I do not believe it. It would be too much of a coincidence. I think that this relation of the Milky Way to the other galaxies is a subject on which more light will be thrown by further observational research, and that ultimately we will find there are many galaxies of a size equal to and surpassing our own." So in the 1940s and onwards, we had the makings of another great debate in cosmology. On the one hand, some wanted to argue that the universe had a definite beginning and had expanded from a single point of space at a single moment of time in the past, and that we were witnessing the evolution of a dynamic, changing universe. But this theory threw up issues. The estimate for the age of the universe was contradicted by the apparent age of the Earth, and it seemed to need for us to live in a weirdly large galaxy. The point I'm making here is that it's certainly not the case that as soon as the universe's expansion was discovered, everyone immediately inferred a Big Bang from that and our whole cosmology emerged directly from it. Most people, with the possible exception of Lemaitre and George Gamow, who first came up with the idea of a Big Bang theory, were not actually convinced that this Big Bang had really happened at all. And this is how Fred Hoyle was able to dismissively coin the term Big Bang on his radio broadcast at the start of our series, and confidently proclaimed that all the observational evidence was against the idea that the universe had ever begun in the first place at all. The story goes that Hoyle, along with two other physicists, Herman Bondi and Tommy Gold, were watching a movie called Dead of Night. This is a horror movie about a man who has recurring nightmares and goes on a retreat in the countryside to help him get over it, where various horrifying antics ensue. It has a circular plotline. At the end of the movie, the main character wakes from a nightmare and decides to go to a cottage in the countryside to get over his nightmares, just as the movie began. Clearly this movie was very influential on a lot of other movies that have come out since, and some science fiction too. But it was also influential on the three physicists, with Gold suggesting, what if the universe operated in the same way, with no beginning and no end? Whenever you join the story, it would always look the same because of this looping nature of it. This would be a kind of perfect cosmological principle. Not only does the universe look the same in whatever direction you look, it's isotropic, or whatever position you're looking from, because it's homogeneous, but it also looks the same throughout all of time. An extra symmetry, then, which is not broken by the universe having a definite ending or beginning, evolving along a straight line, because instead, it's a perfect circle. This in turn gave rise to the idea of the continuous matter creation, the idea that matter is continually and constantly being created to fill in the gaps as the universe expands, eventually giving rise to a universe that always looks the same, forming new galaxies and stars as the old ones are whisked away by the expansion of the universe. Hoyle introduced something called the C field for creation, and argued that this continuous creation of matter was actually driving the expansion of the universe itself. The idea is that the universe expanding corresponds to a kind of negative energy, an anti-gravity, if you will, something that is repelling matter from other matter. As new particles are created in this creation field, they have positive energy and exert a gravitational force. So the idea is that there's a balance of energies here. The positive energy that exists in the form of new particles is balanced by an export of negative energy as the universe expands to other parts of the universe. In this way, the gravitational force from the new particles being created is balanced by an overall anti-gravity that makes the universe expand. And so, in Hoyle's argument, the process overall would conserve energy. Hoyle's theory did require matter to be spontaneously created, but only the odd hydrogen atom's worth every few cubic light years of space every so often, so not at the kind of rate that you'd really need to be able to observe. Hoyle also felt that the most likely particles to be created were neutrons. Given that they were electrically neutral, you wouldn't need to worry about the universe becoming more charged or less charged over time. Free neutrons, when they're left alone, also eventually decay into protons and electrons, the constituent part of hydrogen atoms, which are then forming the building blocks of stars as we know and love today. While Hoyle and others were developing the theory of a steady-state cosmology, developments were being made in astronomical observations as well that cast new light on earlier theories. Fritz Zwicky is another in the cast of characters that we have to introduce. He made an enormous number of contributions to astronomy. In 1934, he was the first person to coin the term supernova, and suggested that supernovae were explosions resulting from the transition of ordinary stars into neutron stars. For more on this, the very first episodes of our show in 2017 covered the life cycle of stars. He also suggested that these high-energy supernovae might be behind the origin of cosmic rays, these super high-energy particles that bombard the Earth's atmosphere from outer space. When the idea was first proposed that space was expanding due to the redshift of the distant galaxies, Zwicky was one of many who rejected it. He instead argued that you could explain the redshift-distance relation if you assume that something was happening that was causing light to lose energy as it travelled. That way, light that's had further to travel, that's gone from further galaxies, would have lost more energy by the time it reached us, which would cause its frequency to shift further and further into the redder portion of the spectrum, without requiring its wavelength to be actually expanded by expanding space. This was part of a class of theories that existed at the time called tired light, the idea being that photons can't quite keep up the pace as they travel across the megaparsecs between galaxies. In the early history of cosmology, there were plenty of such theories floating about. Perhaps light was losing energy due to a sort of gravitational friction with the surrounding matter, or due to interactions with electrons in space. Zwicky's particular theory of tired light was well posed and well described enough to be falsifiable by observations, and when better telescopes demonstrated that it was contradicted by the evidence, he eventually gave up on it. He was renowned as an original thinker, to the point that some of his theories were incorrect, and he often tried to find solutions to problems in astrophysics that no one else had noticed, in quite a counterintuitive way. Unfortunately for Zwicky, this meant that his theories weren't always taken that seriously. Stephen Maurer wrote about Zwicky, quote, "When researchers talk about various different problems in astrophysics, they all start the same way. Zwicky noticed this problem in the 1930s, but back then nobody listened." He is best remembered by history, however, for one particular contribution that drew on a couple of different lines of evidence. So again, we're talking about coming up with a new theory to explain some interesting discrepancies in observations, which was something Zwicky was very good at. First was the problem of the rotating galaxies. Studying a number of different rotating galaxies, Zwicky was concerned that the stars at the edges of the galaxies appeared to be moving too quickly. As you know, for something to rotate, it requires a force that pulls in towards the centre. The gravitational attraction between the Earth and the Sun, for example, keeps the Earth rotating around the Sun and determines the orbital period about that rotation. This is, of course, because gravity is centripetally pulling the Earth in towards the Sun. You can experience this yourself if you swing, say, a weight around on the end of a string. The faster you swing, the greater the centripetal force that you'll need to keep rotating the ball around. For stars contained within galaxies, that centripetal force is provided by gravity. If you're a star at some radius away from the galaxy's centre, the force of gravity pulling in on you depends on the mass of the galaxy contained within the radius of your centre. So you can imagine that you're on the edge of a sphere, all of the mass within that sphere, it acts as if all of the mass within that sphere is concentrated at the centre, pulling inwards. The same is true of Earth, by the way, or indeed any spherical object. The force of gravity keeping you on the ground is the same as if the whole mass of Earth out to the radius you're at was concentrated at the centre of Earth in a single point. In other words, if you know the mass of the galaxy, and the mass profile of the galaxy, i.e. the density of stars at different radii, then you should be able to infer how fast the stars on the edges of the galaxy are going to be rotating. You should be able to infer the rotational speeds of the stars at different distances from the centre. The problem is that the stars appeared to be rotating too quickly for it to be explained by the visible mass of the galaxies that you could infer from stars and luminous dust in those galaxies. Indeed, if the stars were actually rotating at the speed they appeared to be and the galaxies had the mass that they seemed to have, the stars should be flying off into outer space without enough force to keep them bound into this rotation. The only explanation would be if there was some extra invisible force pulling them into the centre of the galaxy harder, which can keep them rotating. For Zwicky, this was evidence that not all of the matter in the galaxies was visible. There must be some matter that we couldn't see. Dark matter, in other words. Using a similar principle, this balance between the kinetic energy of rotational velocities and the gravitational potential energy of a set of objects, known as the virial theorem, Zwicky next looked at a different scale. He looked not at individual galaxies, but at whole clusters of galaxies. Galaxies can form clusters which might contain up to 1,000 galaxies which are loosely bound together by gravity. Zwicky once again carefully measured the velocities of galaxies in the cluster, and once again he found that they were moving too quickly for the cluster to hold together. Once again, if you took everything at face value, you would conclude that the cluster must surely fly apart, unless there was a lot more mass in the cluster and a lot more attractive gravity binding it together than was actually visible. So Zwicky had yet another line of evidence for his dark matter. You will remember that cosmologists had also theorised that the universe was probably flat. They had noticed that the density of matter in the universe appeared to be around 1/10 of what was required to make space flat with no overall curvature. And many simply assumed that because 1/10 was so close to 1 in cosmological astronomical terms, the universe probably was flat in reality, and there was probably simply just a lot of matter that couldn't be seen out there. So even though Zwicky was considered a bit of a crank on this dark matter idea for much of his career, the idea did indeed have legs. Dark matter could explain why galaxies rotated as quickly as they did. It could explain why clusters of galaxies could still hold together, despite how quickly individual galaxies were moving around within the cluster. And it could explain how the universe could still be flat overall, even though there didn't seem to be quite enough visible matter to make it so. Of course, these days, Zwicky's dark matter is a major component of the universe that is critical to our understanding of cosmology and astrophysics. These were not the only developments that were being made in understanding the cosmos in this time. One major discovery helped to start to resolve the cosmological age problem we described earlier. You'll remember that the original distance measurements that Hubble relied on for distant galaxies relied on the Cepheid variable stars, which have that characteristic relationship between their luminosity, how bright they are, and the period of their pulsation, which is what allows us to figure out how far away they are by measuring properties of the star. The only problem is that Hubble had actually been measuring two different types of star, with different relationships, and then treating them as if they were the same. The discovery of these population 2 Cepheids meant that it was determined that galaxies were actually further away than had previously been thought. If galaxies really were further away, then it meant that Hubble's constant was different. The rate of the universe's expansion was slower than was previously thought to explain the redshifts that were seen. And this in turn meant that the universe could be a lot older, in the model where it was expanding. Just like that, overnight in 1952, when this result was announced, both the apparent size and the age of the universe doubled, and it suddenly didn't seem quite so absurd that the universe might have started after all. That big problem of an Earth that was older than the universe was gone. So in the 1940s and the 1950s, you essentially have this competing series of new measurements arising and changing our understanding of the universe. More and more refined measurements slash the value of the Hubble constant, first from 500 km per second per megaparsec, down to 250, and then even lower. Measuring the Hubble constant has become a question of fundamental properties of the universe. Its age and its size and so on can all be inferred from this measurement. As the apparent value shrunk, this meant that estimates for the age of the universe were getting progressively older. At this stage, the job of determining these distance scales in the universe had effectively passed on to a new generation. Hubble himself died of a stroke in 1953, but his PhD student, Alan Sandage, became his scientific heir. As he wrote himself, and John Gribbin recounted, quote, "I felt a tremendous responsibility to carry on with the distance scale work. Hubble had started it, and I was the observer and knew every step of the process that he had laid out. It was clear that it was going to take 15 or 20 years. So I said to myself, this is what I had to do. If it wasn't me, it wasn't going to get done at that period of time. There was no other telescope, there were only 12 people using it, and none of them had been involved with this project. So I had to do it as a matter of responsibility." When Sandage took on the responsibility of correcting Hubble's estimates and determining the true size and age of the universe using his methods and the new understanding of Cepheid variable stars, he was just 27 years old. In the process, he discovered another error that Hubble had made. In using the Cepheid variables to calibrate the distances to stars, Hubble had assumed that other bright objects were also stars. But the higher resolution telescope, now in use, showed them to be clouds of hydrogen gas known as H2 regions. The low, blurry resolution of earlier telescopes was what had made them appear the same as stars. But in actuality, the H2 regions were brighter than the stars that Hubble had compared them with, and so the galaxies were really further away, and this again affected the distance scales that Hubble had been trying to determine for the far-off galaxies. As Sandage continued to work, correcting more and more errors throughout the 1950s, the value of the Hubble constant continued to decrease. Sandage was also able to add more candles to the toolbox. Using Cepheid variable stars allowed astronomers to measure distances up to around a distance of 5 million light-years. The H2 regions, once they had been properly categorised and understood, allowed for distance measures up to tens of millions of light-years. Measurements of the distance to a cluster of galaxies called the Virgo cluster allowed us to expand to 65 million light-years away. And Sandage was eventually able to obtain estimates for distances that were beyond 300 million light-years, using entire galaxies and their estimated luminosity as standard candles. This finally was far enough to be sure that the redshift distance relationship really held over these vast cosmological distances. Sandage's corrections gradually chipped away at the value of the Hubble constant until he estimated it was around 75 km per second per megaparsec, which would correspond to a universe that was around 9 billion years old in the theory of the day. Clearly this is getting a lot closer to the presently accepted value, although even then it was still not quite old enough. But this didn't resolve the issue, because just as Sandage's corrections increased the apparent age of the universe, astrophysicists' estimates for the age of stars also increased, as more about their physics was discovered and understood, and different types of stars were observed. A particular type of star cluster, known as a globular cluster, was estimated to be well over 10 billion years old. So there's this race between the different ages as the apparent age of the universe in an expanding universe theory changes and the rate of the globular clusters changes too. It gets very difficult. Furthermore, Hubble's constant taking this value would still mean that the Milky Way and the Andromeda Galaxy were unusually large galaxies in the grand scheme of things. They would both need to be much larger than any of the galaxies found in the Virgo cluster, for example. So this again offended that classic cosmological principle that there shouldn't be anything too special about our particular galaxy. Or at least, if there was, we should be able to explain why. On top of that, not everyone accepted Sandage's way of calculating the Hubble constant. Different astronomers with different observations and different techniques, alongside different ways of accounting for unknowns, like how much light was being absorbed by dust in the universe, were coming up with different estimates for the Hubble constant, many of which were higher than Sandage's. The contradictions implied by the apparent age of the universe, then, were kept alive for several decades, which in turn fueled a continuing great debate between the steady-state theory of the universe and the Big Bang theory. This is of course where we began the series back in episode 1, with Fred Hoyle confidently declaring to the nation in that radio broadcast in 1949 that the so-called Big Bang theory was really a load of nonsense, and that the battle had been won by steady state. Despite his declaration, though, the real battle between the steady state and Big Bang was just getting started into the 1950s. The steady state model was really probably the orthodox theory at this point, which few astronomers really disbelieved. But as ever in physics and in science more generally, people rarely get the really amazing credit for simply confirming a theory that was already believed to be true. There were some astronomers who were still gunning for the steady state theory, in the hope that they might be able to disprove it and throw cosmology into chaos once again. Happily, there was a way to tell the different theories apart with observations. If the steady-state theory was true, well, the average density of galaxies in the universe should be the same everywhere. In other words, take any region of space that's large enough, count the number of galaxies, it ought to be the same. This is because, as we've described in the steady-state theory, galaxies are being created by this constant creation of matter in empty space, and therefore the density of the galaxies is set by the rate of creation of matter in empty space. Since this has always been the same, and since the universe is static and eternal in this model, we would expect that this density of the galaxies, as well as this rate of matter creation, would be constant. That's kind of the whole point of the model, right? That regardless of expanding space, you'll always see the universe around you looking the same. However, if the Big Bang theory were true, this wouldn't be the case. If the universe did begin at a single point in time and had expanded out from a point, you would expect that the average density of galaxies would have been greater long ago. And indeed, if the Big Bang theory is accurate, you would expect the gaps between galaxies to be getting larger and larger over time in the way that we described. Initially, loads of galaxies close together, eventually they're all spread out. Luckily, we have the option of looking back in time when we make astronomical observations. In fact, we're always doing so because of the finite speed of light. If you're looking at light from an object that's 1 million light years away, you're seeing the object as it was 1 million years ago because of the time that it took for the light to reach you. Consequently, the further you look out into the universe, the further back in time you can see. At that time, following on from the development of radar in the Second World War, radio astronomy was being developed. Telescopes were being constructed that could detect radio signals from outer space. As you probably know, radio waves are the longest wavelength of electromagnetic radiation that exists. A radio wave is simply any piece of electromagnetic radiation, any photon, with a wavelength longer than 1 millimetre. It was discovered that some galaxies were emitting much more of their radiation in the form of radio waves than visible light, allowing these galaxies to be detected by radio astronomy at truly vast distances, at very, very high redshifts. This therefore allowed astronomers using these new radio telescopes to look at vast distances and also way, way back into the past. At that time, it wasn't clear how you could measure the distances to these far-off radio emitters, but it seemed a reasonable guess that the fainter ones might be further away than the brighter ones, simply because of the age-old principle that further away sources of light appear less bright. With this in place then, you now have a mechanism to try and prove, or disprove, the steady-state theory. Are the far-off radio galaxies more densely packed in space than the nearby ones? If they are, then it suggests that galaxies were closer together in the past than they are now. A clear indication that the Big Bang theory is correct, and the steady-state idea is wrong. On the other hand, if the density of these galaxies appears to be the same throughout all of time, even as we look way back into the past by examining these far-off galaxies, then the steady-state theory survives. This debate rumbled on through the 1950s and well into the 1960s. The first study that tried to count these radio galaxies dramatically declared that it had proved the steady-state theory wrong in 1955. Then flaws with that study were discovered and another study seemed to be consistent with steady-state again. In the early 1960s, as radio astronomy improved, it seemed likely that the battle would continue to rage for a little while, but these faint radio galaxy studies were gradually starting to pile up evidence in favour of the Big Bang theory, which no longer had its same cosmological age problems, and against the steady-state model. This was the state of play then for cosmology in 1965. The great debate still raging between a steady-state universe and one that was expanding from a single point in time, with a finite age and a finite size, even if you might not be able to see the edge of it. The surveys of these radio galaxies were hoping to finally settle the argument, but the observational evidence was still unclear enough that there was still a big debate going on. Next episode, we're going to continue this primary story, because there's a reason I brought us up to the year 1965. This was one of those serendipitous moments when a scientific discovery was made, an accidental discovery. It would provide a whole new view of the universe, and a priceless treasure trove of information about cosmology for scientists. Even today, we are continuing to probe and explore the full magnitude of this discovery, learning new things about physics with ever more detailed examination of it. I can't wait to tell you all about it. Next time then, we'll talk about that discovery, of static, of silence, and of pigeon poo. Thank you for listening to this episode of Physical Attraction. Remember, you can find us on the web at physicspodcast.com. There you'll find the contact form where you can get in touch with any comments, questions, concerns, things you'd like to hear more of, things you'd like to hear less of, suggestions, praise, criticism, whatever you like. You'll also find the PayPal link there if you want to donate, a one-off donation to us, and links to the Patreon, patreon.com/physicalattraction, where you will be able to subscribe to the show if you wish to help us out financially and to get access to early episodes and bonus episodes of the show. Thank you to all of you who have done so already. I really appreciate it. You can engage with us, of course, in a number of ways. We're on Twitter at PhysicsPod. There's the Facebook page, Physical Attraction. There's the Science Podcast Facebook group if you want to find out more science podcasts. You can, of course, go to the subreddit, which we have now as well, reddit.com/r/physicspodcast, if you want to discuss the episodes of the show with other like-minded people. One of the best things you can do to support the show, if you don't want to do any of that stuff though, is to tell other people who might be interested to listen to it. Every little helps us compete with the celebrity podcasts, which are out there, with their celebrity hosts. This is an independent effort, of course, by me, written, recorded, produced, hosted, researched, etc. So if you want to help us compete with those people, please do tell other people who might be interested in the subjects that we're covering to listen to the show and review us on your podcast platforms of choice. Thank you so much to everyone who has already done that. Until next time then, please do take care.
Thank you.